Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 5, discrete probability distributions. And in these sections, we're going to focus on the binomial probability distributions. Remember in section 5.1, we did probability distribution, but we defined what was random variable and probability distribution. We defined we determine whether the requirements of a probability distribution satisfy. That means probability is between 0 and 1. Total probability, all probabilities is equal to 1 or 100%. And also, the x's are all numerical data, not categorical data. But in these sections, we're going to describe, because we're going to do binomial distributions. That's what we're going on to in this one. We're going to describe a binomial probability distribution and find the probability values for a binomial distributions. We're going to compute the mean and standard deviation for a binomial distribution and then use those results to determine whether the results are significantly low or significantly high or neither. But as we do for each sections, let's see in terms of key concepts what we're going to do. The focus of these sections, because we already introduced the discrete probability distributions, because now, among these various discrete probability distribution exists. One of them is the binomial distribution. That will be our focus and methods for finding those probabilities. So easy methods for finding the mean and standard deviation of a binomial distribution will be also presented. Then we're gonna use in other sections, we will stress the importance of interpreting probability values to determine whether events are significant low, significantly high, or neither. Without further ado, let's talk mostly about binomial distributions. Binomial probability distributions allow us to deal with circumstances in which the outcome belong to two categories, like you have head and tails, acceptable or defective, survived or die, success or failure. You don't have more than two choice. What is the probability? I mean, when you do a free throw, the free throws in a basketball game, it's either in or out. When the best player of the team, basketball team, has the free throws, either the basketball get in or it's getting out. You either get a success or a failure. There is no third options. But a binomial probability distribution result from producing that from procedure that meets the following four requirements. You need to verify that the procedure has a fixed number of trial. A trial is a singular observation. That means, let's say, as I said, you're in a basketball game. There was a foul on a player. So the player, if it's outside of the semicircle, so it's a 3 free throw. So the number of trials would be 3 in this case. The trial must be independent from each other, meaning that the outcome of any individual trial does not affect the probabilities of the other trials. In a basketball game, when you have 3 free throws, the first one, if you miss this first one, doesn't mean you would miss the second one or you would get the third one. So if you have 3 free throws, all have the same probability of success. You can either put it in or put it out. I'm not stretching out the fact that you might be very stressed and the game, is like very intense, like the public, the people who attend, the attendees will make noise, but that's not the case. You have the same probability of success for each trial. That's very important to see. Each trial must have all outcome classified in exactly 2 categories. You cannot have 3 categories, commonly referred to as success or failure. So let's say, for example, if they ask you questions to answer yes or no, that's a probability distribution. That's a binomial distribution because you either say yes for success, no for failure. But if there is a third option, like not sure, I don't know. So if you have three options, then it's no longer a probability, a binomial probability distributions. And also, the probability of success remain the same in all categories. So what you need to see in a probability distributions, remember it, we want you to see these four categories. We have N, that's the number of trials. Okay. We have P, sorry. Can you call it S or S for success and F for failure? But in binomial distributions, we prefer to say P for probability of success. Q for probability of failure. Now, success, if you fail 60%, if you succeed 50%, what's the percentage of failure again? Yes, 40%. Usually, if you know your probability of success, probability of failure would be 100% minus probability of 1 minus probability of success. Failure, you can always find it if you know the success. All right, that's not a problem. And X are the number of success. Okay, so for a binomial distribution, you're definitely looking for these four. You need to make sure you see N, you see P, you can find Q if you know P, and you have X. You need these four informations to consider it as a binomial distribution. Without these four informations, is not a binomial distribution. It can be another distributions because we're going to have some other categories like geometric distributions or Poisson distributions. But to be binomial distributions, two possible outcomes, success and failure. You have a number of trials. Each trial is independent from one another. There is no without replacement, right? And then you have a number of success and you have probability of failure as well. So S and F, success and failure, they are the two possible category of success. I just show you, but we prefer to use P for probability of success and Q for probability of failure. N is the number of trials. So here you see X is specific number of success in N trials. So X can be any whole number between 0 and 1. And N, inclusive. Remember, don't forget it's inclusive. Probability of success in one trial is P. Probability of failure in one trial is Q. P of X, we call it probability of getting exactly X success among N trials. Questions, make sure that you understand that the word of success as used here is arbitrary and does not necessarily represent something good. Either the two possible categories may be called the success and the success as long as the probability is identified as P. When using a binomial probability distribution, always be sure that X is the number of success and P probability of success. You need to make sure you use X and P in the sense that they both refer to the same category being called success. So when we said the word success doesn't mean, because it's all depends of your interest of at what you are interested to. Let's say, for example, if you are interested to the probability of the probability of someone get involved in an accident is 55%. So that could be the probability of success. Accident is not a good thing, but because you focus, that's your focus. Your focus is on the probability of getting involved in an accident. So that would be your success. However, in real life, is not a good thing. 50% guidance, it's something I'd like you to look through when selecting a sample as in a survey, for example. We usually sample without replacement. Sampling without replacement result in independent events. Remember, we did dependent and independent events in the previous chapter. If you missed it, please look through it again. So sampling without replacement result in dependent events, which violates the requirement of a binomial distribution. However, we can often treat the event as they were independent by applying the rules of 5% guidelines, right? So the 5% here guideline for the cumbersome calculations when sampling without replacement and the sample size is no more than 5% of the size of the population, treat these selections as being independent, even though they are actually dependent. That's what we're gonna do. But let's see it very quick in a very short examples, not a very short examples, because this examples is huge, many questions on it. What we need to do here, determine whether the given procedures result in a binomial distribution or a distribution that can be treated as binomial. For those that are not binomial and cannot be treated as binomial, identify at least one requirement that is not satisfied. So remember, in order to be that binomial distributions, you should be able to identify N, P, Q, and X, and each N is the number of trials, and each trial is independent from one and each other. You know, the probability of success is the same for each trial, so you need to verify that. In a peer review center survey, 3,930 subjects, the ages of the respondents are recorded. So, you know, the age, they don't give you any information like you to see two categories as success and failure because they don't tell you which one it is. That's not a binomial distribution, not a binomial distribution. All right. Now, look at the second one. That survey of 3,930 subjects were asked if they have ever fired a gun. The result consists of two outcomes, yes or no. Because you only have two outcomes, yes or no. Yes, definitely, it's a binomial distribution. If it's binomial distribution, because you know, you have two possible outcomes, yes or no. You have a probability of success and a probability of failure, and you have the number of success and you have N. All right. So that's very important to see it. But the first one, remember, the reason why it's not a binomial distribution, each of ages has more than two possible outcomes. Now, let's see for C. In a US cellular survey of 500 smartphone users, subjects are asked if they find abbreviations such as LOL, LOL, or BFF annoying, and each response were recorded as yes, no, or not sure. You have three answers. Do you feel like it's a binomial distribution? No. Three answers cannot be a binomial distribution, so not a binomial distribution. Not a binomial. Not a binomial distribution. Each response has more than two possible outcomes because there are more than two possible outcomes. So the Wizard method gender selection that Diaz and Dog developed by the Genetics and IVF Institute was designed to increase the likelihood that a baby will be a boy. When 291 couples used the Wizard method and give birth to 291 babies, the genders of the babies are recorded. Well, at this point, when we said the gender of babies being recorded, you know, we need to verify if it's binomial. Yes, because, you know, it's either a boy or not a boy. You have only two possible outcomes because it's either a boy or not a boy, probability of success or a failure, you know, at birth, right? You're either boy or not a boy. So in this case, yes, it's a binomial distribution. Let's see the last one. The Senate members of the 116th Congress include 75 males and 25 females. 40 different senators are randomly selected without replacement, and the gender of each select senators is recorded. Now, remember, because you do it without replacement, the probability of success is not the same, right? Probability of success is not the same. In this case, it's not a binomial distribution because probability of each trial is not the same. Because guess what's going to happen with the probability of success? Okay, probability of success, if to choose the first one, for example, 40 out of 100, 40 different senators are randomly selected, 40 out of 100. Now, the next one would be out of 99 after you pick up the first person. So you're going to have 99. So the probability of success is not the same for each trial. Let's go with another examples very quick. In this particular examples, sorry about that. We are asked, okay? We are asking in this example, so what we're gonna do, answer the questions designed to help understand the rationale for the binomial probability formula. So what you see here, there are a standard test such as STA, SAT, ACT, or MCAT typically use multiple choice questions, each with 5 possible answers, A, B, C, D, E. So you have 5 of them, one of each correct. So probability of success is what? Yes, so probability of success is what? Yes, is 1 out of 5. And what is probability of failure? Yes, 4 out of 5. So no matter what you find when you do these divisions would be the correct answer. So remember, for us, if you do 1 divided by 5, it gives you 0.2. So that means this one would be 0.8, okay? So let's answer the questions very quick because we need to see what type of questions they ask. The first questions would be, we need to find the probability, you know, they said use the multiplication rule to find the probability that the first 2 guessed are wrong and the third one is correct. So if you do the first 2 wrong, so that means probability, you know, the first answer wrong, the second answer wrong, but the third one is right. So for us, it's like we have 16 out of 125. I guess that would be 5 times 5 times 5, right? So if you have 16 divided by 125, it gives you 0.128. Now, look at the second answer. What the second answer tells us, in this answer, it tells us beginning with wrong correct, because remember we said probability of PC, WWC, W for wrong, C for correct. Okay, so now look at B. Beginning with WWC, make a complete list of the different possible origin of 2 wrong answers and 1 correct answer. So they said if the answers are wrong, correct, that's the first one. We can have wrong, correct, wrong, that's the second one. We can have the first one correct, but the other 2 wrong, right? How many can we have more than that? Yes, that's 3. No matter what you do, the answer, the probability, so those are all different possible one, but the probability would still be 0.128 because only 1 answers and 2 incorrect answers for each of them, right? For each of these combinations. Now, look at C. Based on the preceding result, what is the probability of getting exactly one correct answer when making three guesses? Well, if you make a correct answer, in the first guess, to get one correct answer would be 128. The second guess would be 0.128. And the third one would be 0.128. If you multiply the probability by 3, you only need to multiply it by 3 or add it 3 times to itself. Okay, it gives you 0.384. That's the first one. All right, so we just began with this section, so we are warming up, but probability distributions, okay, binomial distributions, we can either do it using formulas because that's where we're gonna start with. We need to proceed with three methods for finding probability corresponding to random variable x in a binomial distribution. The first method involves calculation using a binomial probability formula. This is what you got here. Binomial probability formulas, we can use it. Remember, we said n factorials, and sometimes you can see it as different ways of writing p of x. In some books, you're gonna see, you're gonna have nx times p power x times q n minus x, or you can see it also as combinations ncx times p power x times qn minus x. Remember, binomial distribution, you always need to look for n, p, q, and x. I mean, these four. N is a number of trials. X, the number of successes among n trials. P, probability of success in any one trials. Q, probability of failures. And remember, probability of failure, you always subtract the success from the total to find the probability of failure. So this is the formula we're using to compute the probability distributions. That's one of them. Of course, we have some other methods that involve the software or calculator. That's the one I'm going to show you how to use calculator to do the same, and watch out for my next video on how to use TI-83 or 84 to compute probability distributions. We said also that there is another method that is just a tables. If you have the book with you, you can just go in appendix table A-1 to see the tables you can use. All right. If using technology that automatically produce binomial distributions, that's why we recommend you to solve, as many exercises using the formula, but later we would use calculator or Excel to compute it. We're gonna do with the first one here. Remember, to find the probability of success, we said it's NCX P power x q n minus x. The reason why you see this one, remember, if you have ncx, this is the combinations, n factorials over n minus x factorial. So I believe in this formula, we have n minus x factorial. So that's something wrong going with this one. Apologize for this. It shouldn't be that way. So it should be probability of success equal n factorials over n minus x factorials times x factorials times p power x times q n minus x. So, as soon as you start doing some examples, you will see how different it is. Let's go with the first examples here. Here, what you see, I may make it smaller because you already read it. Let's make it smaller so we can have enough space to do as many as possible. Let's make it font 14. If you're okay with that, and I'm okay with that. Okay. All right. I'm trying to get as much space as possible. For the first examples, A, it says, okay, 40% of consumers believe that cash will be obsolete in the next 20 years based on the JP Morgan Chase, assuming that 8 consumers, because they said, well, 40% of consumers, they're not going to need the probability given must be probability of success here because it's the probability of success is P is 0.40. What do you think Q would be? Yes, 1 minus P. So that means 1 minus 0.40. So it's 0.60. So that's Q. So we have P equal this one, and we have Q equal 0.60. What is N? Because you need to find NPQX. What is N? Yes, N is 8 because they said 8. Okay, I've randomly selected. Randomly means it's very important to see this because everyone has the same probability of choosing. There's a find the probability of that exactly. These keywords is so important. You see exactly, you see at least, you see fewer than, you see no more than, you see none. Okay, you see at least. Okay, at least, so those are keywords you need to know for inequality. But the first one said exactly probability that X is exactly equal to 6. So the good news when you have exactly, you can simply use the formula that we know. And because for us here, exactly 6 for us, X is 6. N is 8. So looking at this formula here, for us, we can say we have N 8, combination 6. Okay. P of X is 0.40 power X. What is X? X is 6 times Q of X, Q is 0.60 power N minus X. N is 8 minus 6. So we have 8C6 0.40 power 6 times 0.60 power 2. Now, you can do it manually, or you can choose to do it using a calculator, because I showed you before how to do these combinations using calculators. Now, let's say that, for some reasons, probability of, you'll see this, sorry, you see this, we're going to have probability. You're going to have probability for us is like 8 factorials over 8 minus 6 factorials times 6 factorials times 0.40 power 6 times 0.60 power 2 that you can eventually do in the calculator. Remember, NCX or NCR from your calculator is not that difficult to see. Of course, you can do it using your calculator. For this one, answer, when you use your calculator, answer would be 0.0413. 0.0413. If you want to do this one using TI 83 or 84, I'm going to put 84. So first of all, check on your calculator where you see distribution. Then after distributions, because it says exactly, you're going to find binomial. You go down and you're going to see binom PDF, and in the parentheses, you're going to put N, P, and X. N in this case would be 8. Remember, you have N to be 8 and P to be 0.440 and X to be 6. And once you do that, hit OK. answer would be from your TI-84. So that shouldn't be that difficult for you to do. I'm hoping you can look through it to do it. Now, let's go for B as in boy. Okay. For B, it says, find the probability that at least 6 of the select consumer believes that cash will be obsolete in essence. At least 6. At least 6 means the X must be greater or equal to 6. That means you need to take at least X equal to 6 plus X equal to 7 plus X equal to 8, because N is 8, we're going to stop there. So meaning you need to do all these when X is 6, when X is 7, when X is 8. We're going to do when X is 6, we're going to do 8, 6, 6, 0.040 power 6. You know what? I'm going to put it at the bottom because I feel like I won't have enough space for it. If we do it here, it would be 866, 0.40 power 6, because X is 6, 0.60 power 8 minus 6, plus 8C7, because you need to do all of them, times 0.40 power 7, 0.60 power 8 minus 7, okay? Plus 8C8 times 0.40 power 8 times 0.60 power 8 minus 8. So that's how we're going to proceed to do these computations. And of course, as I said, answer would be something you do with your calculator, where you do 8 factorials over 8 minus 6 factorials, 6 factorials, doing it with your calculator, times 0.440 power 6, 0.60 power 8 minus 6 is 2, plus 8 factorials over 8 minus 7 factorial, 7 factorial, 0.40 power 7 times 0.60 power 7 minus 8 minus 7 is 1, plus 8 factorials over 8 minus 8 factorials, that 8 factorials, 0.40 power 8. 8 minus 8 is 0, 0.60 power 0. So when you do all of this, I believe answer, when you do all of this, at least 6, answer would be 0.0498. 0.0498. Don't forget, as I said, if in this case, for this particular answer, if you use calculator, after you do for TI 84, please, you do this DISTR from the calculator. Then you do binom CDF. Okay. When you do binom CDF, first of all, because you said at least, you need to do subtract from 1. So you do, it would be by 1 minus binom CDF. Okay. And remember, CDF would be NPX again. So in this case, because at least, okay, because we said at least 6 is included. If you want, these answers would be subtract from 1, N is 8, P is 0.40, and X would be 5, okay? Don't forget about it. You can find it this way. We have until F to do. Probably I may not do all of them because I just want to show you how to do it. But let's suppose I erase all of this. I do copy paste, so to save time. Okay. Let's suppose I remove only AB. So I need space, that's why I remove AB. Now it says, okay, find the probability that fewer than 3. So look at here, fewer than 3 here would be what? I'm gonna use green. Fewer than 3, that means probability that X is less than 3. To be less than 3, that means, remember, is probability that X is equal to 0 plus probability that X is equal to 1 plus probability that X is equal to 2. And for us here again, that would be 8. N is 8, right? N is 8. Remember, N is really 8, okay? So that's N. N is 8. So 0.040 power 0, 0.68 minus 0, that's the first one. 8C1, 0.40 power 1, 0.60 power 8 minus 1, plus 8.2, 0.040 power 2, 0.60 power 8 minus 2. So final answer for this particular one here, because we're doing fewer than 3, answer would be 0.315. Okay, I try to save time by doing it this way, but I'm hoping you see it, because for B here, we said no more than 3. No more than 3, that means 3 is included. We're gonna do probability that X is less or equal to 3, because we said no more than, do not exceed 3, but 3 is included. So we're gonna take the same answer. The only thing we're gonna do to it is to start with 0, X equal to 1, plus X equal to 2, plus X equal to 3. Then you do each of them separately, all right? And, you know, we're gonna, once you do that separately, you would find the answer, because you said no more than 3 is 0.594. Remember here, answer after you do this in TI-84, because it says less than, you don't need to subtract from 1, is binom CDF. Do it in your calculator with NPX. You know, for us, NPX is like we have 8, 0.40, okay, and 3. All right. The same for this one, because it says no more than 3, that means, you know, we need to stop at 4. We do binom CDF. PDF is when we said exactly. CDF is when it's inequality, like less than, no more than, all right? We know is NPX, and we said N is 8, 0.40 for P, and X, we're gonna say 4 because 3 is in it. All right, none. What's the probability to have none? So that means probability that X equal to 0. You know, the only thing you're gonna do with this one is X equal to 0. That means probability that X, because they said find the probability that none of the selected consumers believe that cash would be obsolete in the next 20 years. So we're gonna have 8C0, 0.40 power 0 times 0.60 power 8 minus 0. All right, remember 5 power 0 is 1. Any number raising to power 0 is 1, okay? I don't want you to consider it 0. So for 19, this probability would be 0.019. 0.0168. D, find the probability that at least one of the selected consumers believe that cash. Now, look at what happened in this example. We said at least one. When you said at least one, that means you need to do 1, 2, 3, 4, 5, 6, 7, 8. Because for this one, the difference is like, remember, n is 8. We need to stop at 8 for it. But our problem, it's going to take forever to do. If we said at least one, that means probability that x must be greater or equal to 1. So you need to do 1, 2, 3, 4, 5, 6, 7, 8, or you can do 1 minus probability it's equal to 0. So if you remove 0, that should be fine because we already did 0. So if it's 0, then it's 1 minus 0.0168. If you do it that way, then answer become much easier for us, right? Much easier for us if we subtract the answer from it is 0.983, right? 0.983, okay? Of course, this all depends of the approach you use and, using the calculator. As I said, for the calculator, in a different video, I'll show you using a TI-84 online, but this link, you can just hit TI-84 online. Unfortunately, if I hit it, it's gonna send me to a different screen that I need to show you differently. But you know what? I am gonna do it instead, all right, using it differently. So what we can do with this, of course, I'm gonna show you later what we're planning on doing. Now, let's continue with some other examples because most of all is the same type of questions you're gonna have for all of them based on the, for this one, based on the Society for Human Resources Management, all right, 36%, 36% of human resources professionals are at companies that reject jobs candidates because information found on their social media. So for us, probability of success is 36. What is the probability of failure? Yes, 0.64 because, that's make it 100%. The next information to find is N because you have to have PQN. If 25 human resources professionals is select at random, right, would 14 be a significant high number? So what we need to do here is really do probability that x is greater or equal to 14. You imagine if we do that, we need to do probability that x equal to 14 plus probability that x equal to 15 plus probability that x equal to 16 plus probability that x equal to 17 until you get to probability that x equal to 25. Or the best to do in this case, at least 14, you need to do distributions from your calculator. Then after distributions, you do by 1. Sorry, because I need to do, because at least is greater. So you need to do 1 minus binomial CDF because NPQ or NPX, sorry, NPX, where N is the 25, P is the 0.36, and X would be, in this case, 13. So if you do that, of course, at the end, the answer would approximately, the answers would be approximately the same, okay? In this case, the answers would be approximately the same. If the answers are approximately the same, then we know the probability would be 0.0326. All right. The questions asked in this case Sorry about that. Would 14 be a significantly high number to be a significantly high number to be to be at companies that reject job candidates because of information found in the social media? In this case, we would say that yes. It's a yes. Why? 14 would definitely be a significant high number. 14 will be a significant significantly high number. I don't need to write everything. You understand it? Please go slower on this and you can write it. Yes, 14 would be significantly high number. The probability of 14 is 14 or more, right? Is 0.0326, which is, low than 5%, right? All right. Because I'm gonna write it because the probability of 14 or more, at least 14, is 0.0326. That means 3.26%, which is lower, which is less than 5%. Right? I'm hoping you got this because we do a lots of significantly high, significantly low. All right. Now let's go with another examples because in this one, we said that based on a Harris poll among adults who regret getting tattoos, 20 says that they were too young when they got the tattoos. So remember, what you provided is probability of success. If you know success, then you can find failure. And the next step is to identify, because this is success, so n minus this give you failure. The next step is to identify n, assume that 5 adults, okay, who regret getting tattoos are randomly selected. So we know n is only 5, which is great, and find the indicated probabilities. For A, find the probability that none of the selected adults, that means find the probability that X is equal to 0. So if X is equal to 0, remember X equals 0, that means C 5, 0, okay, P power. Remember that the formula for binomial distributions is NCX P power X Q N minus X. Okay, so if you do that, okay, if you do that, what you would see, we're gonna do 0.20 power 0, 0.80, which is Q power N. N is 5 minus 0, of course. Something you can do with your calculator also. Answer would be 0.328. Remember, if you do calculator with TI-84, after you do distribution from the calculator, remember you need to do binom PDF. You put N, which is 5, probability of success 0.20, and X is 0. Answer would approximately be the same. B, find the probability that exactly 1. This is exactly 1. So again, X here equal 1. So probability that X equal 1 would be 5C1 0.20 power 1 times 0.80 power 5 minus 1. 5 minus 1 is 4. You can do it. And at the end, answer would be 0.410. Again, if you do calculator, because exactly you use PDF, binom PDF, N is 5, probabilities of success 20%, and X is 1 to do with calculator. Now, let's go with C as in cat. Find the probability that the number of selected adults saying they were too young is 0 or 1. So 0 or 1, remember, it's not 0 and 1. 0 or 1, meaning is the addition with probability that X is equal to 0 plus probability that X is equal to 1. Because we already did these two. If you do these two, all you need to do is to add them up, these two information, right? So you add 0.328 plus 0.410. Answer is 0.738, right? Last question. If we randomly select 5 adults, is 1 significantly low? Number will say that they were too young, right? Again, here, look at part C. Significantly low, you cannot say that. It's not unusual because look at the probability to select at least, is 1 is not significantly low because 1 is more than 5%, right? It's not unusual. So no, definitely no. So we're gonna put no. But as an explanation, I would tell you the probability that we find in part C is not too small. So part C is not too small, right? So 1 is not unusually low number. So no, it's like really a big part. So we can consider this one, and moving forward, with this, what we need to learn from here also is why, as we said, we can use in this case, because we're going to use a lot of Excel, and we're going to also use TI-84. But in the meantime, because nowadays you cannot do anything in statistics without using technology. So follow me to see other videos covering, how to find probability distribution or binary distribution using TI-84, TI-83, or Excel. Now, for these sections, we include also formulas for finding the mean, variance, and standard deviation from any discrete probability distribution. We did that in section 5.1. A binomial distribution is a particular type of discrete probability distribution. So we could use the same type of formulas, a little bit different, right? But we know the values of N and P, then this is very easy. I think this is the easiest way to find the mean, because remember, probability of success is given. We know if you know P, then Q is 1 minus P. Easy to find the standard deviation, the variance, and the mean. We said that significantly low, remember, it's 2 standard deviation below the mean. Significantly high is 2 standard deviation above the mean. In between is not significantly low or high. All right. So let's assume in this particular examples, assume that hybridization experiments are conducted with P's having the property that for offspring, there is a 75% probability that a P has green parts, right? So for us, once we identify the 75%, remember this, the 75% right there, for us, easy to say this is P. What is Q, please? Yes, Q is 0.25. Next step is to identify what is N. Oh, you see a group of 10. In this particular example, N is 10. Now, what they ask you to find probability. No, they said they find the mean and the standard deviation. So that's what they ask you to find. Remember, if you know the variance, then you know the standard deviation. So for us, what we're gonna do, we know in the first examples, mean mu is NP. What is NP? That means 10 times 0.75. So the mean in itself, if we find the mean, for us here, the mean is 7.5. All right. Now, we said also for the standard deviation, sigma is square roots of NPQ. That means square roots of 10 times 0.75 times 0.25. If you take this square, multiply all of this, and find, remember Q, what is Q? Q is 1 minus P for 7.25. It gives you 1.4. Okay. Now, use the range of rule of thumb to find the values separating, to the values separating the separating results that are significantly low or significantly high. We need to verify this. Values, we always need to do significantly low or significantly high. Remember, you do 2 standard deviation below the mean. That means 7.5, 7.5 minus 2 times. You know what? I need more space. Let's do it the other way around, right? 7.5, we need to do it the other way around. I'm going to just copy, paste, so I have enough space to do it. Yeah. Let's do it the other way around. All right. So I'm going to keep it this way, okay? When I keep it this way, the first thing I'm going to verify, because I have enough space for now, let's do it down here. For B, we said we need to do the mean minus 2 standard deviation for significantly low. Oh, minus 2 standard deviation. That means 7.5 minus 2 times 1.4. Answer for this one would give us 4. Answer for this would give us 4.7. Significantly high. Okay. Significantly high is standard, the mean plus 2 standard deviation, 7.5 plus 2 times 1.4. Answer, when you do significantly high, it gave us 10.3. Right? So significantly high is between, values between, okay, not neither okay, we said neither is between 4.7 and 10.3, right? Now let's see for C. The C, we said, is the result of 9 peas with green pods result that is significantly high. Do you think it's significantly high if it's 9? No, it's not because it's not greater than 10, right? 9 is not greater than 10.3, right? Because it's not greater than 3, the result is not significant. It's not significantly high, right? So it's not significantly high because it's not greater than 10. Now, if we go with the second examples, because as I said, I'm trying to do some of them, and of course, I'll leave the other ones for you. Okay, so let's erase that part. Okay, let's erase that part. I'm trying to erase as much as possible. Okay. I'm gonna keep it on the same place. But for us now, in the second examples you see here, okay, with the second examples, we see that it's the same type of questions, it's the same types of questions because n here is 16. All right, if n is 16, the mean A, mu is NP, so meaning 16 times 0.75. You can check your calculator. That would give you 12. If the standard deviation, remember what the standard deviation is square root of NPQ. So sigma would be square root of 16 times 0.75 times 0.25. Remember to take the square root of it. If you don't take the square root of it, then it will be just variance. It's not really significant. So the standard deviation is 1.7. Now, again, for B, remember significantly low. I'm going to put SL for significantly low. Remember, is the mean minus 2 standard deviation, 12 minus 2 times 1.7. So it should be below 8.6 and significantly high. That means it should be above 2 standard deviation. That means 12 plus 2 times 1.7. All right. So it gives you, from your calculator, 15.4. So doing this like that, 15.4, doing this like that, of course, they ask you for it. If it's between, then it's not. It's neither. Now, do you feel 7? What's happened with 7? 7 is significantly low because it's less. See, significantly low. 7 is significantly low. You know why? Because it's less than 8.6, right? If it's all between 8.6 and the other one, it's not gonna work. Okay, so those are things you need to verify, because they said the questions is 7 significantly low. Yes, that's yes. It's a yes. It's a big giant yes. All right. That's what we did. We answer questions again here. Remember, we use this again to answer a few questions. Remind you about the formula again. Remember, you can use calculator or Excel to answer them. And there are 2 extra exercises, but I'll do only one of them before we part ways. In this particular examples, we're going to into that involve binomial probabilities, finding parameters or determine whether values are significantly high or significantly low using the range rule of thumbs and probabilities. Of course, we're going to do that. But looking at this exercise, you know, using calculator would be way better. Using technology, I would say technology, not really calculator, but I would say technology is very important because here, what they ask you is to verify, always find your P, your Q, and N. What is P here? What is the probability of success? 13%. If you have 13%, then 87% is probability of success, right? Of failure. So where is N? Oh my God, N is huge. It's 3, 4, 5. In any way you cannot do that using a calculator. So what they ask you to do for these 345 M&Ms, so use the range of rule of thumbs to identify the limit separating numbers of Brown that are significantly low or significantly high, because in order to do that, of course, you need to find the mean. The mean is NP, that means 345 times 13. What the mean would be, because you must find the mean. If you find the mean is 44.9, and you need to find the standard deviation, which is the square root of NPQ, which is square root of 345 times 0.13 times 0.87. Take the square root. Don't forget the square roots. And what is the standard deviation in this particular case? Standard deviation is 6.2. Okay. Now we have the standard deviation, and it's like we have everything. I believe from there, of course, we can go and do everything. So for A, remember we do significantly low. That means mu minus 2 standard deviation. That means 44.9 minus 2 times 6.2, because we need to use a rule of thumb to do that. When you subtract this, okay, when you subtract it that way, you find 32.4. And if you do significantly high, mean minus plus 2 standard deviation, that means 44.9 plus 2 times 6.2. Final answer for this also, when you add it, it's 57.3. So doing these two, if I do these two, all right, so 32.5 and 57.3, that's the two we're gonna find. The result, the questions is use a rule of thumb to identify the limit separating numbers of M&Ms that are significantly low and significantly high. Based on the result, do you believe that 36 Brown M&Ms is significantly low? No, 36 doesn't fall below 32.4. 36 doesn't fall below 32.4. It's not significantly low. Okay, I need to verify it that way. Now they said find the probability of exactly 36. Oh, no, look at that. So we we can do exactly 36, but for the other ones, that would be terrible because if you do B, it's gonna be probability that X equal 36 because we have N, we have everything. We know that will be 345 for N, C 36.13 power 36 times 0.87 power 345 minus 36. Yes, expect that you cannot do these ones without calculator. Look at that, all right? So of course you can do it because without a scientific calculator, because you have an exponent that would be over 300, right? So you cannot do it manually. You must have a calculator. Once you do that, answer must be 0.0241, okay? 0.0241. Now, let's say for C, find the probability of, oh my God, all right? So to do this one, you definitely need to go with calculator because you said 36 and fewer or fewer. That means you need to go 36, 35, 34. So it's better you use calculator where you do distributions in the calculator. Then you say binom CDF, okay? And you go with N, which is 345.13 for the probability and 36. That's the only way you're gonna find this answer. Hopefully, you can use it to find it because the probability would be giantly long. 0.0878 would be the answer. Now, for D, which probability is relevant for determining whether the result of 36 Brown is significantly low or significantly high? We can just give some explanation. It's part C is relevant because the 36 is not significantly low, right? You see, we don't even find less than 5%. And the result, for E, what do the results show us? About 13% claimed by Mars. So at this point, you really you don't have enough evidence to going against the 13%. So it's non-conclusive. I'll stop here, and the last questions is exactly the same in a different video. Remember, I'll show you in how to use TI-84 to compute those probabilities. Look for these videos coming soon. You take care. I'll see you in a different video for section 5.3.